What's up, y'all? Welcome back to another LeetCode Path to Pro video. Today it is Tuesday, June 20th, 2023, and I'm solving number 144, binary tree pre-order traversal. It's an easy. I was looking at the daily for today, and I was like, I think I could do it, maybe, but it was kind of hard, and I'm tired, so I'm like, I'll give myself an easier one. Not saying that this is super easy and I'll be able to do it, but the concept is definitely easier. It's pretty simple. So the problem is, given the root of a binary tree, return the pre-order traversal of its nodes values. So root is, so here we got a tree where it's 1 and then 2 and then 3. Output is 1 to 3. Nope. Okay. And so I think pre-order traversal. Pre-order. Visit the root. So visit the root, traverse the left, traverse the right. Okay. Yeah, so that's what we're doing. So I like to do these problems recursively, where we'll have a helper function, and what do we need to pass into the helper function? We need self and root, I think, right? At some point, we'll be calling helper on the root, right? We just return this? Maybe. And then we'll say if root equals, or we're going to say if not root. Return false. And we can also say if root equals 1. Okay, yeah, I think that should handle the base case if they just gave us, they give us an empty tree. We're just we're not doing it. And then we're gonna have our helper function, and that's gonna be we need to make a list. Do we need a result list? Boop. And then we result.append node.val. I'll do root.val. And then we run helper on root.left. And then root.right. Is that what we do? No. Okay. I might just look at a solution here. Because these are like, let's see. So, put the result up here. Oh, self.helper. That's how you call it. Self.helper root. And then return result. Will that run it? No, because we gotta have a result. And I did input the self. Okay, so I did some things wrong, but so we don't want to pass in the root value, passing the node we're at, but we just start it at the root, right? Our root is our starting node. Okay, that makes sense. Oh, and he has if node. That's smart. Cool. I'm glad I looked at this. Shout out who or she. Shout out whoever did this. Mazang. If not root. And then we have our result. Guy, yeah. Yeah, that should work. I didn't pass in the result. Tab now. False. If not root, return. Root return an empty list. Yeah. Okay. Cool. So no. I don't know what that was. Yeah. So let's just go over what's happening here. Let's do 4. Then over here we have 2. Well, this can't be 1. We'll do 3, 2. Jeez Louise, man. 1. This is hopefully it'll kind of explain what's going on. 4. We can go 7 and 6. Okay, so what's happening is we're saying, okay, if there is no root, we're just gonna return an empty list. But obviously there is a root here, so that's not gonna go. It's not gonna activate. Then we're setting a result to be an empty list. Then we are calling the helper function that we made and passing in the root and the result, which is an empty list. Our helper function has 3 conditional, or I don't know the terms of conditions. Self, which is just like the Python thing. Node, which is the node that we're at, and we're passing in root, so we're starting at the root and the result. So then we're checking if the node exists. So this is how we break out of this function, because it'll stop running when there is no more nodes. So first we're going to append the node. So PreOrder is like, it's like this, where we have our result, which is empty to start. Pass in the root, 3, boom, we append the 3. Then we go left, boom, pass in 2. Would it be 4 next or 1? I wonder. I think it's 1. Then we go 1, boom. Okay, now we go down the right subtree, 4, boom, 7, boom, 6. Da-da. So we're going 3, appending it, then we're going left subtree, appending 2, going left subtree, appending 1, jumping back up, going to 4, appending it, going to 7, appending it, going to 6, appending it. So yeah, and then the time complexities of this, let's think. I think, I'm going to give a classic answer. I think it's O of n time, I think, because we're going through each node once. And then the memory complexity, because we're using a recursive solution. A recursive just means you're calling the function. So, like you make a function and then you're calling it multiple times in your solution. I think that the memory complexity of that on the stack is O of h, where h is the height of the tree, because that's how many times we're gonna have to call this function. So yeah, cool. That's it. Not too bad. Not too bad. Yeah. Thanks for watching, guys. Have a good day.